work in motion applications, and when they say motion, usually they're referring to something that relates to DRT, dirt. Distance equals rate times time. I actually prefer to think of it as rate equals distance divided by time. The reason why I prefer this is just because it's usually in miles per hour. Miles is distance, hours is time. And when you're driving, that's kind of what you're looking at, is your rate of speed, or speed, which is a rate. And then to me, that's how I think about this formula. But mathematically, they usually show it something like this one. But modeling work problems, they give us some of this stuff right here like this. I don't really care to look at it like this stuff down here. Really, what you can see here is that it says it's T over A. I guess it's time needed for the work to be done alone. For work type problems, I kind of like to look at it as jobs over, I guess, how much time it takes to do a job, or however many jobs it is, right? So for example, if they said you can do 5 jobs in 8 hours, then I would set up some kind of fraction like 5 jobs in 8 hours. But we don't necessarily label these. I mean, you could, just to kind of keep track of where stuff is. 5 jobs in 8 hours. But when we're talking about work problems, why are we seeing addition of these types of fractions? It's because we're looking at taking one person and bringing in another person and saying, well, now you two do the work together, and then we'll see how long it takes. But this is kind of a general format or formula that kind of helps us with that. It says that it equals 1. It doesn't always equal 1. Again, it's how many jobs can you do in that many hours? But we'll have to find out, okay? Read and reread these several times to really think about how they set up. Is it required to set up a formula like we're seeing right here? I don't think it necessarily is, but sometimes it's helpful to see it, especially if they say, well, you do a job in this much time, your pal does a job, but they don't tell you how much time it takes, but they know that together you can do it in a certain amount of time. Okay, well then how long does it take for your pal to do the job by themselves? Okay, well that may be a little bit more difficult to formulate, but we'll see. Okay, but do expect to read and reread these, think about it, and then hopefully that helps you to set up. And that's true also for the distance type problems that we're talking about, the motion applications. Yeah, so these all 3 of these, they're exactly the same. They're just set up differently, right? Like you can see here, this formula right here, they just did it as a 1 over A times the T, or 1 over B times the T. So this formula has been kind of rewritten this way, and then of course you can factor out the T, and then you can just divide both sides by T, which then ends up being like this. So this, I said I kind of like to use this one. Really, this is the way that we end up seeing it, I guess. Go ahead and take that one. I'll put a star next to it, because stars are pretty. So you can paint your room in 12 hours. Your friend can paint the same room in 20 hours. How long does it take for both of you to paint the room that should be if you are working together? Okay, well, that's a good question right there. Expect more of that, these typos in the future. So, all right. So we got 2 people working together, right? You got you, and then you got your friend. I'm going to put pal because it's a shorter word. And I literally do not want to write those extra 3 letters. Unfortunately, though, I've got to write this long word. We got to look at what happens when you do it together. Okay. Now, let's focus on each person. And again, I'm looking at doing this, looking at jobs for some number of hours. Again, when we say hours, it's not like, well, I guess it kind of is, but it's hours. How long does it take you to do that job? All right. So when we look at you, if this was a 9th grade class, I'd say, not that anyone wants to look at you, but in any case, so You can do one job. So in other words, you can do one. You can say job. I'm going to put room on this one. Again, I'm labeling it, but the label isn't really necessary right here. You can paint one room here. Okay, that's the job that you're doing. Well, how long will it take you to paint that room? Up here it said that it's going to take you 12 hours. Yeah. One room, you can paint this one room in 12 hours. Now, thankfully for us, your pal is going to paint the same room. So again, we're going to look at your pal here now. And we know your pal can do the same exact room. So that's one room, that's the same job. Well, how long will it take your pal? Your pal's apparently much slower than you are, or more thorough. We're not really.
That probably is only good for drinking.
Yeah, up here it said, hey, your friend, they can do it in 20 hours. So again, we're kind of setting up a bit of a fraction right there, right? Now the question says, we want to know how long it takes for both of you to paint. That's why I should have said both, because it's a shorter word. But together, you're going to do the same room. So as a fraction, you're looking at one room. It's the same exact room. We just don't know how many hours it's going to take. So I'm actually going to define the variable. X is how long it takes hours together. Yeah.
So you can put it as T, 1 or X, whatever.
Yeah. I like to use X just because I'm used to it. But yeah, use whatever you want. T, for some reason, if you want to use A or whatever you want, it's fine. Yep.
Or L.
Yeah, I don't mind.
Q.
Boom, do it.
Nice.
Just be careful with L's and O's. That's all that I recommend there. So, well, how long will it take you to work together? X hours. We don't know how many hours that's going to be. Okay.
This is plus equal.
Yes. So we're going to take your work and add it to your pal's work, and that's how long it should be together. Okay. So this is how the fraction. Is this a rational expression like we've been seeing? Not quite, because we're not seeing a binomial or trinomial here, but it still is an equation of those rational equations here in this case that we have to solve. Now, so here's what I'm going to do. I'm going to rewrite that the equation, okay, just without any of the labels. So it's 1 over 12 plus 1 over 20 equals 1 over x. Now remember, just like we saw last lesson, it's an equation with a variable, particularly in the denominator, right? So what we would like to do here is get rid of all of the denominators so we can rewrite the equation without any denominators. So at this point, I'm gonna force the denominators to match. And when I do this, personally, I like to force the letters to match if there are any. And I do. I got this x right there. So if I can just get the x's to match, I can worry about the numbers later. We have a little bit more experience, hopefully, with the numbers by now. But if we just can get the x out of the way, right? So I just want x's to match. So I'm going to give the 20 denominator an x. But again, if you multiply that by x, you got to multiply the numerator by x also. All right? And then the 12, it also is missing the x denominator. So I'm going to multiply it by x. And if I multiply it by x, I've got to multiply the numerator by x. Okay? So this is where I'm at right here. So I got the x to match in all of the denominators, which is a great start. And it was fairly easy for me because I didn't have to think, what I got to multiply these by, okay? But now I've got to do it with the numbers. So I've got 12 and 20. I would like a common factor right here, common denominator here. And it doesn't have to be the lowest. Remember that? It doesn't have to be the lowest. It just has to be common. Now, a common way to do it is just to say, well, I'm going to take the 20 multiplied by 12, 12 by 20, multiplied by x by 12 and 20. I'm actually going to go for the lowest common one just because it's going to make the number smaller, which hopefully makes us feel better inside, but I don't know. The lowest common denominator is the lowest common multiple for the numbers. So I'm looking at 12 and 20, right? Now, in the past, you'd say, you know what, I'm going to list multiples of 12 here, and that would be 12, 24. I know it's small, but there's not very many. 48, yeah, 60 is the one. Okay, so we get to 60 right there. Well, what do I got to multiply 12 by to get to 60? 5. Boom. So I got to multiply, again, both numerator and denominator by 5. And that will guarantee a denominator of 60. Okay, so now I said 60. I kind of jumped to that conclusion because I know 20, a multiple of 20 is also going to be 60. It's the third multiple of 20. So I'm going to multiply 20 by 3, and then I've got to multiply the numerator by 3. All right? And again, the purpose of this is to force, I already forced the x's to match. Now I'm trying to force the numbers to match. The last problem here, because we get so used to just adding fractions like this, it's like, hey, I got my denominators to match. No, we need this one to match too. Don't forget, it has to be all the denominators, because a lot of the times this is what students miss right here. They miss this one right here. They say I got 5x over 60x plus 3x over 60x equals 1. No, you didn't have the common denominator, so you can't do that yet. So we're going to do that by multiplying the x by, well, we wanted those denominators to be 60, so I'm just going to multiply by 60. That was pretty easy, because the coefficient of that x, specifically in the denominator, is 1. But if I do it to the denominator, I've got to do it to the numerator. All right, so this is going to give me a new equation. I'll work here to the right, and then I'll work down. But what I get then is from the first fraction, 5 times, again, I'm just looking at the numerator, 5 times 1 times x is 5x. 5 times 12 times x would be 60x's. And by the way, once you get enough experience, I think a lot of students would skip this step, and if you do, that's fine. But if you never want to get that much experience, then I get that too. But in the numerator of the second fraction, right, 3 times 1 times x would be 3x's all over. 3 times 20 times x would be 60x's. So again, we're seeing that the denominators are, in fact, matching. And this would equal 60 times 1, which is 60, all over 60 times x is just 60x. So we have gotten the denominators to match at this point. And now, just like we saw in the last lesson, I'm now going to rewrite the equation, but without any denominators, okay? Because once the denominators match, you're just dealing with the same size pieces, and so it doesn't matter if you add, subtract, multiply, or divide them. So now what do I got? I got 5x's plus 3x's. It's kind of a jacked up plus sign, there we go, equals the 60. Right, because I got rid of completely the denominators. Well, if we had started with this equation, we may not have rejoiced because it's still math, but we probably would have thought, yeah, I feel like I can do that. So let's continue there. From the 5x plus 3x, I know I can combine these like terms, these x's. So 5x's plus 3x's would be 8x's. This equals 60. Last thing I need to do here to solve it, again, x. What does x represent? It represents, we defined it up there, x is the hours that it would take to do the job together. So I'm going to divide both sides here by the coefficient of 8. So this would be like doing 8 of those right now. It would take you, if you did the 8 of the jobs, it would take 60 hours. But we only want one of the jobs, right? How many hours would it take to do one of them? I'll go back to green because that's the color I defined x is. So x equals, well, I should have my calculator, 7.5. So again, x was hours together, and this is a word problem. If you see a word problem, make sure you label it, okay? So it's 7.5 hours. And the fraction's okay on that one, which I think would be 15 over 2. You know, if you really want the fraction, but I think the decimal probably is a little bit more clear. That you probably wouldn't go to someone and be like, it takes 15.5 hours for me to do this job with my friend, but you're welcome to do that with people. So now this one was nice, right? It's like, okay, we just got some x's here. We just combined the like terms here at the end. But again, a lot of the students struggle with just setting this up together. Again, you only got 3 parts to it. You got your friend, and then you got doing it together. And then understanding that these fractions kind of set up as how many. I put up here jobs because it may not be painting a room, right? It may be pipes putting out water, or I don't know what they're going to come up with, but something. It may be just a different job, right? Like you two can build a house. You can build a house by yourself, and I don't know, whatever. If you do a job in 12 hours, they're not saying what we're doing. It's just some kind of job. Again, you could say homework, and if you could work together on homework, so be it. But if you can do a job in 12 hours, and with the help of your friend, you can do it together in 3 hours. Notice it's not telling us how long it takes the friend to do it, which is why that produces this question. how long would it take your friend to do it alone? So right here, again, if you want to use a t, I like to use x's. I'm going to say x. X should pretty much always represent what you're trying to find on this one, and it's how long it's going to take. And I'll type this one in just because it's it's kind of wordy there, but this is going to be x is how long it takes your friend to do the job alone. And again, we're looking at, when we say how long, sometimes we get that mixed up with distance, especially in a lesson like this one where we're going to be looking at, well, distance with the motion applications. So I'm going to specify. This one we're looking for number of hours it takes your friend to do the job alone, all right? So once again, you got two people working on this thing. Or you got you got your pal, again, and then you can do it together. So I'm just going to put both because it's a shorter word, and I literally do not want to write all the letters. So you, your pal, and then you can do it together, right? Well, you, up here it says you can do the job in 12 hours. Now it didn't say you could do 5 jobs in 12 hours. So when I set up this fraction, my numerator, right, it's one job. You can do one job, but it will take you 12 hours. 12 hours. Your pal, it says, how long would it take your friend to do it? Again, that would represent one job. But again, we do not know how long it will take your friend to do that job. So x, I don't really need to label the x. I mean, I'll label my answer because I've already defined it as how long it takes your friend in hours. The other information that it gave us is that together you can do it in 3 hours. So that would, again, it's just the one job, and it will take 3 hours. Okay, so if you take your work and add it to your pal's work, you get both your work. And this is how that sets up for us, okay? So I'm going to rewrite this again. So I've kind of set it up with labels just so, again, we can see where stuff goes in the fractions. But they have to be set up this way, okay? Because your work is, it's a ratio of the jobs to hours. But think about this, if you flip all these fractions, you get 12 plus x equals 3, and then you get some kind of negative number. So it doesn't work, all right? So because your pal can't do it in negative time. So let's go ahead and set this up, all right? So I got 1 over 12 plus 1 over x equals 1 over 3. But just like we saw in that last problem, I do need common denominators so I can just wipe them out, right? And like I said in the last problem as well, I would like to see them have common x's first. Now, if you would like to focus on the numbers first, do it. I just don't recommend doing both at the same time because you can start getting things jumbled and mixed up. So I'm going to apply to the 12 denominator, I'm going to give it an x. But if I give it the denominator an x, I need the numerator to have an x as well. Same thing with the 3 denominator, it's missing the x. But if I multiply the denominator, I need to multiply it by the numerator. And again, I'll just emphasize this. This is really x over x. I've just multiplied this fraction by 1, which means I have not changed the overall value of the individual fraction. Same with this one. And it's going to work the same way with the numbers that I'm going to be applying. So I know that 12 is a multiple of 3 and this phantom 1. But so I'm not going to actually work with the 12 because it's the denominator I'm shooting for on this one. But notice that I took some time right here to actually look at this and think about it. You're probably going to have to do the same thing. Is there algorithms for this? Yeah, you could just say, well, I'm going to multiply 12 by 3, and then this 1 by 12 and 3, and then the 3 you'd multiply by 12. Now that goes back to just a quick way to force denominators to be the same. But if you do it with a little bit of thought, usually it ends up being, I don't know, decent numbers at least. So let's go and take those, and let's get them multiplied. So the phantom 1x there, I'm going to multiply it by 12. But again, if you multiply in the denominator, please multiply in the numerator. Otherwise, you've just really changed the equation. You're going to get it jacked up. So that's a 12x. See the 12x there in the denominator? This one's 12x. But the 3x right there, that's no good. Can I make a 3 of 12? Sure. Just multiply it by 4. But if you do it to the denominator, do it to the numerator as well. Right? So what does this give us? Well, let's look. Let's put this in there. So my first fraction here, so that's, again, this would be your work. You could do X jobs in 12X hours. Your friend, your pal, they could do 12 jobs in 12X hours. And then together, looks like you could do 4X jobs in 12X hours. Now, I was kind of interpreting these fractions. You don't have to, because the purpose of this whole exercise right here was to get the denominators to match. They do match, and so I'm now going to rewrite the equation, but without any fractions, only the numerators on this, okay? So here's what I get. I'll rewrite it. I got x plus 12 equals 4x. Now again, if we had started with this equation, we would have been happy, but we didn't. So here we are. We gotta finish off this equation. I'm gonna get the x's on the same side. I'm actually gonna zero out this x, so I'm gonna put my x's on the right. I commonly just put them on the left though. But I'm gonna isolate, in this case, the x's by getting them all on the same side. So I'm gonna subtract an x. It's really a 1x, I mean, if you really wanna see that, but that's gonna zero that out. Drop your 12, which now equals 4x's minus 1x's would be 3x's. And then finally, here, I just want 1x's, right? So this, by the way, is telling us if your friend did the job in this many hours, they'd do 3 jobs, it looks like, in 12 hours. So I'm going to divide both sides by 3. And now I can see your friend, how long does it take him? 3. Sorry, 4. 4 is the, I almost jacked that up. Good morning. So 4, it's going to take your friend 4 hours if they were to do it by themselves. And so unlike the last problem, I guess you're the slow one in this one. But it's good. All right, what the crap are we looking at here? These three equations are exactly the same equation. They've just been manipulated. So if you want distance, you can just use this formula. If you want time, you could solve for this formula. You can solve with this formula. Or if you want rate, you can solve with this one. But you kind of have to figure out which one you're going to have to use for these motion applications, okay? So again, are you going to pick this up very quickly? Probably not. But if you do enough of it, you will. But what I'm saying here is you may have to take some time. You may even have to do some guess and test. Like maybe you thought it was rate, but you see that doesn't work. Okay, well then go back to time and then do that one. Okay, that didn't work. Try the distance equals rate times time. We've seen applications of this, like the rowing up the stream or the airplane going on a trip and then back against the wind, right? Like, okay, if your distance is the same, you said distance equals distance, and if that happens, that's fine. But sometimes, again, you just may have to add these together. We'll see. Here we go. A boat, which moves at 25 miles per hour in water without a current. So we know the speed of the water without a current for some reason. But it goes 60 miles upstream. That's the distance it's going upstream. And when we see upstream, I'll make a note of this just so we can remember this. But upstream is against the current. All right, that'll be important to know. And then it goes 60 miles back again. Now, if it's going upstream first, then if it goes back, that would be when it goes back. Let's see if I can do this right. When it goes back, it is going with the stream, the current. I think they call that downstream. There we go. So when you go back, you're going downstream. And the current is pushing you towards your destination. But we do know that it goes, when you go back again, it looks like it's going to take you 5 hours to go that 60 miles. But what we want is the speed of the current to the nearest tenth, okay? Oh, so I apologize. I was thinking that was just the downstream trip. This is both So, and again, this is the importance of reading and rereading these. But you got 60 miles upstream, and then you got 60 miles downstream, and this is how long it takes you to do both, okay? So I'm gonna separate these. We got two parts to your trip. You're going to go upstream. By the way, I haven't really determined which of those formulas I'm using. Upstream. Okay, then you're gonna go downstream. This is the return trip, or going back, but this would be downstream. Okay, and again, it was talking about time right there. So if you take your time for upstream and add it to your time downstream, this is the total trip. Total trip time. There's a name for that. 3 T's together like that, but I don't know what it is and I don't care. So, I'm assuming that we're looking at the time formula on these, okay? So the time should be the same as taking the distance and dividing it by the rate. D equals RT, yeah, so divide both sides by R, okay? Time is the distance divided by the rate, okay? And again, how do I know this is time? It's because it gave us the total trip in time. Okay, so I'm expecting my upstream time and my downstream time, but it's in relation to your distance and your rate, okay? So if I look at your upstream time, distance, your upstream time is distance over your rate. Your distance, it said you went 60 miles upstream, right? Okay, your distance is 60. You can label that miles if you'd like. But the rate, this is where we get a little bit of confusion because it's like, well, it didn't tell us how fast you were going. And some students just mistakenly say, well, you were going 25 miles per hour, right? Well, you were, but that was only part of your trip, right? That's the boat in still water or without a current. So what we have to do here is we gotta apply the current. And since you were going upstream, you were going against the current. So I'm using the variable c in this case. Again, C should represent what we're solving for. That's the speed of the current. Okay, so I've already got a C with my upstream ratio, distance over the rate. Okay, well that's good. What about downstream? Well, again, I'm looking at it as a ratio because time is going to be distance divided by the rate. Well, it's the same distance though. You went the same 60 miles back again. So that's going to be 60 over, again, you have the speed of your boat because that's your rate, but now you're going with the current, so it's adding to your speed. So that's the representation of both times, both for upstream and downstream. If you add those two times together, the total trip took, it said, 5 hours. Well, yeah, we do want to see a denominator for the 5 because we're going to force the denominators to match, and then we're going to get rid of them. So I can't just apply like those last problems with the work. I can't just say, well, each of these is just missing a C, so I'm just going to tack on a C with the 1. I can't do that because this is 25 minus C, 25 plus C. So we're really looking at binomials on this. So let's apply them as binomials. So I really have two denominators here that I got to worry about. The 1, not so much, right? So I'm going to take that 25 plus C, and I'm going to apply it to the 25 minus C right there. And by apply, I mean I'm going to multiply. Sorry if the writing's kind of small, but this is 25 plus C. I'm going to multiply it there, okay? Because that fraction was missing a denominator, 25 plus C. But don't forget, if you apply to the denominator, you got to multiply by the numerator as well. So 25 plus C there. And so, yeah, sorry this is written poorly, but again, this all is in an attempt to get rid of the denominators anyways. Okay, so now I look at this fraction. It's got the 25 plus C now that we've applied it here. It's there, but we're now missing the 25 minus C. And by the way, this should look like that difference of squares, the end of that, right? So I've multiplied the denominator by 25 minus c. Now I've got to multiply it by the numerator as well, 25 minus c. Okay, so over here on this part of the equation, I have matching denominators, but this denominator over here, which is a 1, which we showed, it's now missing both of them. But I'm going to do one at a time, okay? So I'm going to apply the purple one first, just because I guess that's the one I started with. Doesn't matter which one you start with, though. So 25 plus c. Again, if you do it to the denominator, please do it to the numerator as well. And then I got to multiply it by the other denominator of 25 minus c in both the numerator and denominator, okay? And again, all I've really done here is I've multiplied it by 1 and 1. It's just, what did I want 1 to be? Well, I forced it to be this. Okay, so this one has a 1, and if you're really confused by that, understand that all of these are being multiplied by 1s. It's just we don't have to show them, okay? But what I've done there, I've now forced the denominators to match, which is what we wanted. Because once they match, I don't need them anymore. So I'm going to rewrite this equation without any denominators. So that was in the numerator, the first numerator, 25 plus c times 60. And then that would be added to the other numerator, which was 60 times 25 minus c. And then this equals all that stuff. See if I can just copy it. I'm satisfied with that. Okay. And again, I do apologize. I did put the 25 plus c on the list left side. Hopefully that's not a problem. We know we can distribute from the right parentheses because it's just multiplication. So hopefully that's not too bad. But I am in the process of I need to now be in the process of distribution, right? I've got the 60 first, so I'm gonna have to multiply 60 by 25.
1,500.
Thank you. Got a human calculator here, you know. So, and then 60 times c, 60c. Okay, well, that's the first distribution. Let's distribute this other 60. Well, the good news is 60 times 25 is still 1,500. And 60 times negative c would be negative 60c. And that was pretty good, right? But we got a lot of distribution on the right, so let's get that simplified. I'm going to start with distribution of just the binomials, which some people prefer to call FOIL. And if you do, that's okay. So 25 times 25 is 625. We forgive you, you know. And then we got the 25 times the negative c would be negative 25c. Again, we are expecting this to be a difference of squares there. And then the distribution of this c times that 25 would be positive 25c. See how it gets that? Those two middle terms zero out. And then c times negative c would be negative c squared. Okay, so I did zero this out. I'm not applying the 5 yet, by the way, because I don't want to. Because I would like to simplify the inside here first, which I just did. And now, the inside of that parentheses is 625. Probably gave myself more space than I need. Times minus c squared. But now I will look at the times by 5, okay? Like I said, I'd like to get rid of that. And yeah, we do have some like terms on the left to combine as well. We'll get to that. But I'm going to distribute the 5 there. And yep, I do need more space. So I got 5 times 620. Oh, crap. Typed it in wrong. 5 times 625, 3125. And then 5 times negative c squared would just be negative 5c squared. That's pretty good. All right, this all equals the stuff that we had before, but I know on the left that if I were to combine my 60c and the negative 60c, that just zeroes out. So those just zero out. But what I will then do is I'm going to take this 1,500 plus 1,500, which would be 3,000, right there. I will mention this before I proceed. Okay, you could have kept this like this and then divided both sides by 5 if you wanted to. Again, you're just using principles of equality because now I'm in principles of equality. But whether you notice that or not doesn't matter because you can do it, but you don't have to. Like I did, I distributed. But right in here, what I would like is the c squareds by themselves. So I want that 3125 to be gone. And by gone, I mean zero out. So I'm going to subtract 3125 from both sides. That would give me negative 125 on the left, which now equals, I'm going to drop the negative 5c squared. Okay, because we zeroed out the 3125 in green as we planned. unfortunately. I need more space, just a little bit more. But now that we're at this point, we're going to solve for c squared. Now remember, we do want just c though. That's how we defined it up there at the top. So we're gonna have to do something after this. But first, let's divide both sides by -5. And it appears to be then 25 equals c squared. Well, that's nice actually, because all I've got to do at this point is square root it. Okay, now you could say in this case, c, it could be 5 or -5, but this is a word problem, and so even though the numbers are the same, I don't really care about the -5. I was just looking for the primary root there because it's a word problem. You couldn't say that the speed of the current is -5 miles per hour. I mean, you could if it, because we were going with or against the current. But really, we just want the 5 there. So C, that was the speed of the current, 5 miles per hour. That's all you got to put. But if you want to say 5 miles per hour is the speed of the current, now that I've said it out loud, let's go on. 5 miles per hour, the speed of the, and I would never expect anyone to write all this on a test, but you could. The speed of the current is, I think it was miles per hour, right? 5 miles per hour? Miles per hour, yeah. There at the top, right? So yeah, we're good. So this part, I think, I don't remember seeing this recently. I'm not saying we haven't seen it, but I just don't remember when we did. And so we haven't seen this in a little while. Again, if you got a c squared, you're going to make that a c by simply square rooting both sides. I did change the position of the c, by the way, in the equation. I'll show that extra step. So it would have shown c equals 5 right there. I know, right? So I just switched the c and the 5. I don't know. It makes me feel better inside, I guess. So you can paddle your kayak 6 miles per hour in still water. It takes you as long to paddle 15 miles upstream as it takes you to travel 21 miles downstream. Thank you. Determine the speed of the river's current. Okay, so it's kind of the same question, but it's different. Okay, well how is it different? Because it says it takes you you paddle 15 miles upstream, but it takes you as long to travel 21 miles downstream. And when it says as long, where does it say that? Right here. It's talking about time right there, right? Because we have the distances. Now, we do know that it's 15 miles upstream and then 21 miles downstream. So naturally, you should be traveling further when you go downstream because the current is pushing you, right? Assuming that your paddling speed is consistent for those, however many hours this is, it looks like over 3. And if that's possible, that's great. I know I could go for maybe 5 minutes, but in any case, I'm anticipating this to be some kind of time application on this one, okay? And we know time is distance divided by the rate. But here's what I know, is we do have upstream, right? So we're going to look at upstream. And we know that upstream is that's against the current, my bad. And then we got downstream, that's with the current, that's better. Okay, and again, what we see here, it says that it takes as long. That means in terms of the times, they're equal time. All right. Now, if I'm wrong on this, that's okay, because we'll go back. But I'm expecting this to be time, right? So upstream, they did give us a distance. It took you 15 miles, or you were able to go 15 miles. That's our distance. The distance is the numerator. So you went 15 miles up the stream. That's against the stream. But they also say over here, hey, look, your paddling speed is 6 miles per hour. That would be if the water was completely still. So you're going to take your 6 miles per hour paddling speed, and it appears we're going to go against the current. So that's minus. Your speed is going to be less, so you're going to be taking away speed because the current's pushing against you. Now, I just put the variable c in there. Let's go ahead and define that, right? I'll do it this way. Hopefully it's easier. C is the speed of the current in miles per hour. Because everything right now, as far as I can see, is in miles per hour, okay? All right, and I think that's working. Let's look though at downstream. So downstream, it said you were able to go 21 miles. So for my ratio, my fraction, 21 is the numerator. Now your paddling speed, of course, in still water's the same, but now we're adding the speed of the current. And again, we expect it to be added because you were able to go farther in the same amount of time. That was kind of the point there. So these two ratios are equal. All right, to solve this one, of course, you could just make the denominators match, but this is a proportion right here. Now, what does that mean? It means that you could just use cross multiplication at this point. Okay, so I'm going to cross multiply these, it's going to keep them equal, okay? Now, if you wanted to, just take this side and multiply by 6 plus c, and then this side by 6 minus c, both numerators and denominators, you end up with the same thing on this, okay? So my green multiplication would be 15. Okay, so that's 15 times the, where it's crossed with multiplication, right? 6 plus c. And then on the right side, I'm multiplying, it's 21 times the 6 minus c. So I'm putting the 21 in front just so it looks kind of familiar there. But from here, we have some distribution, right? So I'm going to distribute the 15. In my calculator, 15 times 6 is 90. 15 times c is just positive 15 c's. And this is equal to, let's distribute the 21. 21 times 6 is going to be 126. And then 21 times negative c is negative 21c. So I'm going to use a principle of equality at this point in order to kind of finish solving this. And I'm going to put the c's on the left and the numbers on the right. I don't really care if the coefficient's negative or not because we're going to divide. But that means the 90 is going to have to be zeroed out. So I'm going to have to subtract 90 from both sides. But in addition to that, I've got this negative 21c on the number side, so I'm going to have to zero that out as well. So plus 21c's on the right, but if I do it on the right, I got to do it on the left. So what does this do? Well, as planned, it zeroes out the 90 and the and the negative 21c's. Okay, but what do I get from the c's on the left? Well, I got 15c's plus 21c's is 36c's. This then equals 126 minus 90, which is 36. And then the last thing I need to do here is just make the coefficient of c a phantom 1. So it should read as c equals, and I'll do that by dividing 36 by itself. But if I do it to one side, I'll have to do it to the other side. Now this becomes a phantom 1 right there, but the other side, 36 divided by 36, I need to show that, okay? And this concludes the problem because now we know what c is. C is 1. C, also at the top, we wrote that it represents the speed of the current. So the speed of the current is 1 mile per hour. Boom, that's it. Of course, if you're doing this on paper, you'd want to show 1 mph, and that's good too. Now, some students get to the point where they're like, yeah, Mr. Sal, that's great, but I really want to check. Well, check, okay? So remember, the times have to be the same, right? So the time for upstream would have been 15 divided by 6 minus 1. That's 15 divided by 5. That would have given us 3 time, right? So that's 3 hours upstream. Okay, we should get the same time for downstream. So 21 divided by 6 plus 1 is 21 divided by 7. It's 3 as well. So we put those back in and we checked, and we did find that it took the same amount of time for both. And again, that's using the time formula, distance divided by rate. Let's get started. Gerardo and Jennifer leave the same restaurant at the same time, leaving in opposite directions. If Gerardo travels 5 miles per hour and Jennifer travels 12 miles per hour, how long until they are 85 miles apart? Okay, so let's see. I'm gonna have to reread this one. They leave at the same time. They're going in opposite directions. If Gerardo is 5 miles per hour and Jennifer is 12 miles per hour, so Gerardo is going much slower. I don't know if that's important, but we do have a distance on this one. Well, with that, then I guess I am expecting this to be a distance relationship because our final answer here, or total, is in some form of distance right there. It's 85 miles. Now we know, again, from a couple slides ago, that distance is the same as taking the rate and multiplying it by the time. And in fact, well, they did say how long is it until they are 85 miles apart. So I'm going to say, I'll use t in this case just because it is time. T is the time, how long it takes, I'll put. We got the two distances. We'll go with Gerardo first. Okay, so I'm gonna, because I don't want to write, that's kind of a long name for me, Gerardo, plus I'm not sure I could spell it right. Gerardo, I'll do Gerardo in red. Well, Gerardo, his distance is the rate times the time. Up here it says Gerardo, he's going 5 miles per hour, okay? Now, because we do want the distance, his distance is just, I'm gonna take it, his speed, and multiply it by the time. I don't know the time, but, so I'm gonna just define it as t on that. Okay, so that's Gerardo, that's his distance. Then we also have Jennifer, right? So I'm gonna take Jennifer down here. We'll do Jennifer's in purple. So Jennifer, it says she is going 12 miles per hour, so she can go 12 miles per hour, but we don't know how long she's gonna be doing that for. So I'm gonna multiply the 12 by the t, okay? Now, these two distances should give us the total distance. Which we know is 85 miles. Okay, now, here's the other thing, is their distances are getting farther apart as they travel. So the two distances here, I'm gonna have to add them together, and then that would give me my total. Okay, now you have to do some thought, because I think there's some of these where you end up subtracting them. Could be wrong about that. But again, put some thought into this, and make sure you're doing it. I think I did that right, by the way. I think I'm using the correct variable as distance, right? Or time in this case. So yeah, I'm gonna put that in the video. The distances that they travel are not the same, so that doesn't really help us in an equation. The speeds, they told us the speeds were not the same, so that doesn't help us either. It's the time that will be the same. It's the factor or the variable that it has to be consistent. Otherwise, we end up with two variables, which we don't want. So this one is so great because it's so close to being finished. All I gotta do is combine my terms, the t terms. 5 t's plus 12 t's is 17 t's, and this still equals 85. But then, even then, it's just one final step to solve. All I gotta do is take both of these and divide them by the coefficient, which is 17. So I got 17 divided by 17, phantom 1, t then, t is how long it will take. Well, that would be 85 divided by 17 is 5. Now, how long, this is not how long in distance, it's how long in time. That's why we use t, and time in this case was in hours. It'll take them 5 hours until they are 85 miles apart. Okay, now you can check this as well. Okay, so if this takes 5 hours, Gerardo would have taken 5 hours at 5 miles per hour. 5 times 5 that would have been 25 miles for Gerardo. Okay, now it's not 85, but together it's 85. So if Jennifer takes, she's traveling 12 miles per hour for 5 hours, she would have traveled 60 miles, and then 25 plus 60, it does equal 85. So you can even check these ones when you're doing them to make sure that they're going to give you some truthfulness from the original conditions that were given. Alan and Cassandra are, I know it could be Cassandra, but I don't care, are traveling towards each other from points that are 122 miles apart. If Cassandra is traveling 1 mile per hour faster than Alan, they meet after 2 hours. How fast was each traveling? So this right here is a rate. Their speed is always a rate because it's a distance divided by time situation. Okay, so I know I'm looking at some kind of d over t situation here, I guess. They're traveling towards each other. So again, this time, perhaps it could be a subtraction situation on this one, but we'll see. So we got 2 people. Let's see how this goes, right? I do know that I got Alan. And then on the other hand, we have Cassandra. Okay. And we're going to take those rates. I guess our final situation here is that they meet after 2 hours. So that's our time on that one. I don't know. Right now, just having set it up as rate, I don't know that that's going to be the case on this one. This would mean that they both did travel 2 hours, though. I'm going to put that in. I will. So, okay. So if I looked at the distances, I mean, it looks like they both traveled 122 miles, right? My problem here is that so yeah, they're not actually traveling the 122 miles. You see the importance of reading these and rereading them, right? Plus, if I did that, if I said, well, if I set it up with this rate equals distance divided by time business, not only do I not know how long or how, well, I don't even know the speeds necessarily, kind of. I can say that they're related to each other.
So Alan is.
But, so we do know that Alan's speed, though, the rate for Alan is, so 1 mile per hour. Oh, so there's two ways to do this. You can define a variable for Cassandra, or you can define it for Alan. I guess we'll do Cassandra, is that right? So here's what I mean is, C, I will say, is, want to know how fast, the speed, that's Cassandra's speed, okay? You can do Alan's, by the way. So my variable is including speed in there. So I'm kind of figuring the rate is not going to help me. Again, it's not helping me. It certainly is not helping me set up these fractions with distance divided by time. So I'm gonna regroup, and I'm gonna say, well, that's it's usually distance equals rate times time. And the reason why I'm going there is because we do have a time, right? They're both going to travel 2 hours. And then we do have some kind of relationship with the rates, at least, all right? For example, Alan's rate, or Alan's speed, his speed is like taking Cassandra's, but he's going slower, right? Because she's 1 mile per hour faster, so you'd have to take Cassandra's speed and take one mile per hour away from that. Cassandra's speed is just Cassandra's speed, C, right? That's what we defined it as. And then we found the rates, and then we would multiply that by the time. We know they did both travel 2 hours. So I can just multiply both of these then by 2. Yeah, see how that's kind of setting up pretty good, right? And then the distance that they're going to travel together. So the distance they travel together, yeah, it's set up here is 122 miles apart. But they're both traveling towards that distance, so I'm pretty sure we're adding those two distances. Alan's distance plus Cassandra's distance ends up being a total distance of 122 miles right there. So let's go ahead and get started solving this equation. So let's go ahead and distribute then, because we do have that distribution of the 2. So 2 times C is going to be 2C. 2 times -1 is -2. Of course, we still have everything else. And from here, I can look for any like terms combined. I got the C's, right? So 2C's plus 2C's is 4C's. Now I've got -2, and that's a positive 4C. It's going to equal 122. So some principles of equality now. I'm going to go ahead and zero out that -2, so add 2 to both sides. Okay, so that does zero that out. I can drop my 4C's, which now equal 122 plus 2 would be 124. And then last thing here is to make that coefficient of C a 1. So that's going to show a phantom 1C, but I would divide both sides here by 4. And 124 divided by 4 appears to be 31. Now C, again, what is C? C was Cassandra's speed, right? So that's 31. It appears that they were driving in miles, and this was in hours. So this is also 31 miles per hour, but that's for Cassandra. Okay? Well, Alan is going 1 mile per hour less than that. So Alan's, we're gonna take Cassandra's at 31, and we just gotta take one away from that. Okay, so Alan then is going 30 miles per hour. So this is Alan's speed, right here. And this is Cassandra's speed. Okay, well, if this is true, can we actually check? Well, they met after 2 hours, right? So the distances come together. Alan then traveling 30 miles per hour, which we already figured out, C minus 1. 30 times 2 tells us that Alan then, he would have traveled 60 of those miles. Cassandra, though, she's at 31 miles per hour, so 2 times 31 would have been 62. And yeah, if you take 60 and add it to the 62, you will get 122 miles of distance. So you left your house and rode your bike into town at 9 miles per hour. Along the way, you got a flat, so you had to turn around and walk your bike back to your house, traveling 3 miles per hour. Again, we don't care about how reasonable this is, it's just the math. But if the trip down and back so that's total trip. That means the flat and then the walking home. It's gonna take 24 hours. How far did you get before your tire went flat? Okay, so here's what I got, just to get us started, is the question is saying, how far did you get? How far, that's a distance on this one. If it was time, then it seems like those are being worded as how long, right? So I'm looking for some amount of distance on this one. So I'm gonna use D here as my distance. That's how far did he get before the tire went flat? So my distance, D is the distance, I guess in this case, you left your house, right? So that's the distance from your house to the flat, okay? Now, just as a quick reminder, hopefully this diagram helps. So you got your house right here, and yeah, that's a good enough house for me. If you want to be specific, put a roof over the head. But you're going to take your bike, you're going to ride it over here, and this is where you get your flat. Boom. Okay, so that's the distance from your house. How long is that? I don't know. But I do know that you rode your bike first, and then on the way back, then you walked. So you're going to ride the bike to the flat. Once you get a flat, you're going to walk home, hopefully with the bike and hopefully to fix the flat. But all this is going to take 24 hours, and that's going to be a key point for us. You got 24 hours, apparently, that you did this all in. Maybe no breaks, I guess. So the distance, okay, so we have two different frames of reference here. You got the amount of time that you were biking or distance you were biking. And then you also have whatever you did when you were walking. And then this is some kind of total, right? I guess it's kind of double the distance there. But I guess we're going to kind of have to take these two distances. And so I'm kind of looking at some kind of distance here, right? But how far did you, if the trip down and back took 24 hours, that's going to be important for us, okay? Because that 24 hours, that's the total time for both the biking and the walking, okay? So the biking and the walking are going to be related to some amount of total time, because that's a total that we have, and usually that means that when we take those values, we want them to equal some kind of total time. But the total time, you'd have time walking and biking, so we're gonna have to add those two together, all right? But again, what are we looking at here? Well, we have a total time just directly as 24 hours, okay? So that means for me, we're probably looking at some kind of time formula where it's gonna be distance divided by the rate. Now, D is the distance we don't know. So in these two fractions for biking and walking, they're the same distance, by the way. So you take some distance to bike, you take some distance to bike, you take the same distance to walk. But then again, we got to look at the rates. Well, the rates were actually given to us, right? So up here, it says that you were riding your bike at 9 miles per hour. So it's going to be 9 in the denominator there for my biking, because remember, the rate goes in the denominator. And then when you walk, you're going at 3 miles per hour. So that's going to be divided by 3 right there. If I were to take, because these are times, distance divided by 9 is time biking, distance divided by 3 is time walking. If I were to add those together, I should get the 24, right? Now the D, whatever we solve for D, it's still the distance that you were, how far away you were when you biked or when you were walking. So right here, what I need is common denominators, and right now the 24 has the denominator 1. I also have denominators of 3 and 9. Well, 9 is a multiple of 3 and 1, so I'm going to keep that denominator the same, meaning my biking is just going to stay the same, but I'm going to start doing some stuff with my walking right there. So the walking, I'd have to multiply the 3 and the D by 3, right? So that'd be now 3D over 9. And then also the 24 and the 1. The 1 times 9, again, that's going to give us a common denominator of 9. 24 times 9, I don't know what that is, but my calculator does. 24 times 9 is 216. Okay, so again, we're adding these together, and this should equal the final number there. But from this, I'm going to now change it into a single equation, but without the denominator. So D plus the 3 distances should equal 216. And from here, we just take our like terms and combine them. So that would be 4 of those distances from your house. It's saying it's the same thing as 216. So finally, to solve this, I would just divide both sides by 4. And so the distance from the house appears to be 54. Now that's 54. We were looking at miles per hour, so that's going to be 54 miles right there. That should be our answer. Okay. Now, is it 54? Well, if you're 54 miles away from your house and you're biking at 9 miles per hour, that means you were biking for 6 hours. Okay? If you were walking, then 54 divided by 3 is going to be 18. So you would have walked for 18 hours after biking for 6, and that would total as 24 hours. 6 plus 18 is 24, so that checks. Now, there is another way to do it. I don't know how logical it is, but here's what we know. You got, you know that the biking was 3 times as fast as the walking. So you got, what this tells us is that you have 3 parts of walking and then 1 part of biking, okay? So the walking would have been 3 parts. And then the biking would have been 1 part. Well, what am I talking about 1 part? I'm talking about time, because 1 part of the time and 3 parts of the time. Again, how do we know that? Because biking was 3 times as fast as the walking. If it takes 24 hours, then we can take that 24 hours and break it up into increments. So since I have 4 total parts, biking and walking, I would then take 24 and divide it by the 4 parts. This tells us that each increment is in 6 hours, okay? Now this also tells me that they were biking, because biking is 1 part. They biked for 6 hours, and we already found that out here, right? But in addition to that, the walking would have been 3 times the 6. And again, that's where we get the 18 hours. Well, if they were biking for 6 hours, you could have said, well, 6 times the 9 miles per hour would have given us 54 miles. And then again, we would have confirmed that, because we see now that we were walking for 18 hours at 3 miles per hour. 18 times 3 is also 54. So again, is that the most efficient way to do it? I don't know, but it is a way to do it. And it would have been a way actually without having to put together all this garbage. But again, some students don't understand that, so this is actually the garbage. It's up to you. You left the party early, traveling 3 miles per hour. 2 hours later, Nicole decided to head out and catch up with you. But she's running at 4 miles per hour. how long would she have to run to catch up with you? Now, again, how long generally indicates that we're looking at some form of distance. In this case, since we're going at miles per hour, we're looking at some number of miles. Okay, so right here, we'll say that the distance that she's gonna have to travel is D. That's how many miles just Nicole has to run, right? Because she's going faster than you, she's gonna catch up. Now, of course, there's a backdoor way to do this one. I'm gonna talk about it after I do all this equation stuff, okay? So here's the thing is the distances are going to be the same, right? Because Nicole's catching up to you, and that's a crucial part because in order for Nicole to catch up to you, she has to be at the same distance, okay? So I would be looking at these probably for some kind of distance formula, all right? And we know that distance equals the rate times the time. Now, the two good things that we do know about is the rate and well, we don't know exactly the times, but we can use t as a variable here. So it looks like we may need both variables, or just maybe again, it's kind of like we're gonna have to find out how much time it takes her, and then that will help us to figure out how many miles she's going to have to run. So in order for Nicole to catch up to you, she's gonna have to run the same distance. So again, I'm gonna start with distance formulas on these, okay? So there's two distances. We have your distance, it's you, and then we have Nicole's distance, right? Well, your distance and Nicole's distance, we want to find out where they're equal. We just don't know how much time that's going to take. So again, I'm going to actually have to define another variable. I got t, which is time. Again, in hours. It's how much time it takes for Nicole to catch up to you. Now, for your distance, let's see. We have your rate. It showed your rate as 3 miles per hour. So your distance would be 3 times the amount of time. Now, your time is not how much time Nicole traveled, right? So you will travel the same amount of time Nicole traveled. So I got the t there. Again, that's the time that Nicole travels. So I'm going to specify that here. But you also left 2 hours earlier than Nicole. So you got Nicole's time, but then you're going to add 2 more to that. Okay, and this should be equal to whatever Nicole's time is. We do know that she ran at 4 miles per hour, so I'm going to take 4 and multiply it by the amount of time that she ran. Now, if by chance here you said, well, the t is the time that you ran, well then Nicole's would have been t minus 2, and yours would have been a t right here. But you're going to get exactly the same amount of time. It's just that, remember, the answer wants how many miles, how many miles Nicole ran. So you need to figure out still how many hours that Nicole ran to catch up to you. But this becomes an equation that we just need to solve at this point. So I'm going to distribute the 3. 3 times t is 3t. 3 times 2 is 6. And this still equals 4t. Not 40, but 4t. And last up here, to solve this one, we're gonna get rid of that 3t. So I'm gonna put my t's on the right. Doesn't really matter that it's there. I almost use x, but let's use t instead. So 3t's minus 3t's is 0. I can drop my 6, which now equals 4 minus 3t's would just be, you can show it as 1t, but I'm gonna make it a phantom 1. Now the reason why that is because that should solve the problem. Or it should solve the problem to this point, right? So 6, that's how many hours Nicole ran. But it didn't want how many hours Nicole ran, right? What we want is the distance. D is the distance. So the distance, right? We have the formula. We now know how many miles, or how many hours rather, that Nicole ran. She ran for 6 hours. We know from the problem that she ran at 4 miles per hour. That's a rate. 4 times 6. That's the distance that she ran. She ran for 24 miles, which, if I'm not mistaken, is close to or more than a marathon. But Nicole is going to run for 24 miles, and that would be our final answer right there. But again, we did have to, this one was very different, I would say, because we did set up the distance, but we also had to have a variable in there. We didn't know how much time it took her, but the time was what helped us to actually solve the problem, how many miles that she had to run. How would you know that? Well, again, you may have to do some trial and error on this one. Maybe you set up a time formula in here or a rate formula. But again, the rate was given directly. The time wasn't, right? But again, one of the key factors in this that we need is that she's going to catch up with you. And that is how we made this part of the formula. It was a distance. That's what it means to catch up. It was an equal distance on that one. In the past few problems we saw, it's like, all right, you run a certain distance and Nicole runs away from you. We want to know when you're this far apart, or you're running together and you start this far apart, this kind of thing. But now it was like, well, we need the distances to be the same. Again, all this comes from reading the problem. You notice that I went through the problem, I would say 2 or 3 times throughout this. You may just have to read and reread and reread and reread and reread the problem until you understand what it really wants and then how to set things up. But again, even that, you may have to do some trial and error before you can get to this point where it's like, all right, I see this, I can solve it. I'm not saying it's fun, but it is something you'll probably have to do until you get used to it. All right, this one's going to be very different, kind of, but let's read it first. One inlet pipe can fill an empty pool in 6 hours, and a drain can empty the pool in 9 hours. How long will it take the pipe to fill the pool if the drain is left open? So this one, notice there's no miles per hour, there's no distances, there's time, we got the hours, but we can't tell like a rate on this. The only thing they say here is that it can fill an empty pool in 6 hours, and then it's empty in 9 hours if you drain it. So I don't see anything in terms of distance on this. Again, you could say you got a rate, hours per pool or something like that. But the reason I'm bringing that up is that this is a job application type problem, okay? A job problem, okay? So again, I'm looking for jobs as a ratio to hours on this one. And we got 2 parts to this, right? You can either fill the pool or you can either empty the pool. Okay, so before, when we looked at these job type problems, it was just like you and a pal. But now we're looking at a pool that can be either filled or be emptied. So in filling and emptying the pool, the other thing we'll need to notice on this one, that it's saying how long will it take the pipe to fill the pool, but while the drain is open. So that means we're looking at filling while also being emptied. So that means we're looking at both of those, okay? So if I take the filling and the emptying together, so that means I'm going to put them together. So I'm going to show addition right here, even though in the future we know emptying means it's being taken out. And so if you wanted to, you could, if you wanted to, just make that a minus. Okay, so in fact, you know what, I will stick with that, although what I was going to do is make that plus a negative, which in the end would have just made it minus, okay? So I'm going to take away the emptying because it's being subtracted there. Now, these fractions are going to be shown in jobs per hours. And so I know filling this up, I can fill one pool, and it's a ratio, one pool in, up here it says you can fill it in 6 hours. But then you can empty it, it says in 9 hours, so emptying the pool, again, you can do one pool, empty it completely in 9 hours. And again, this, if you take the filling and then subtract the emptying, then you get both. So you should, with both, you should empty a pool, but we just don't know how many hours that's going to take. So up here, I'm going to use X. You could use P maybe for pool, but I'm going to use X. So X that's going to take, that's how long it will take to fill the pool while the drain is open, okay? Which of course is not very efficient, but now I know X. It says how long, that's hours. Okay, now that I've got that, I'm ready to reset this up just without the labels. So on this one, again, we are subtracting because we're emptying the pool, because it's being taken out, right? We're taking the water out. But now that I got this, I need common denominator. So again, I've got the X denominator here. These ones don't have X's. It's a pretty quick thing that I can just apply there. So 9 times X, but just make sure you multiply it by the numerator and denominator. And then the 6 as well. I gotta multiply that by X. And so the numerator by X. So I've got X's to match. Now I just need the numbers to match. 6 and 9, they're not multiples of each other, but I can find a common multiple of 18 with these. And so that's what I'm gonna do. I'm gonna take these, I'm gonna make it an 18 denominator. So of course the X I could just multiply by 18, and so the 1 by 18 as well. The 9 I'd have to multiply by 2, and so the 1 by 2 as well. And again, the purpose of the 2 times 9 is to make that 18. The 6 though, I'm gonna have to multiply that by 3. Okay, so what do I get out of this? Well, I now have, from the first fraction, 3 times 1 times X would be 3X's. All over 3 times 6X would be 18X's. Okay, and then from the second fraction, 2 times 1 times X would be 2X's. And then 2 times 9 times X would be 18X's. Again, the whole purpose of that last part of this exercise was to get the denominators to match. And now in the final fraction there, 18 times 1 is 18. 18 times X is 18X. So now that my denominators match, I can now rewrite this, but without any of the denominators. So that means I now have 3X minus 2X equals 18. And yeah, I right now have 2 like terms that I can combine. 3X's minus 2X's gives me 1X, which means that we have, in fact, already solved for X. Okay, so I'll just make that a phantom 1. But what did X represent? We said up here it's how long it will take to fill the pool while also draining it. So it looks like it will take 18 hours to drain the pool, and I'll specify that with a sentence here, just because hopefully that makes it nice. Okay, so hopefully that kind of makes sense right there. Now, would you have to write this on a test? Of course not. We just expect this, and of course the work. But however you say it, if you want to take the shortcut and just say 18 hours is good, but if you want to write it like that, that's fine too.